Thank you again. It's really a pleasure presenting this to you. And Transat actually is the funding agency for this project. And I'm the PI of this project. And my graduate students who are working in this project are Roxana Hussain and Walid Omar. Roxana presented yesterday a poster on the same topic, and today I'll be presenting to you. So the title, I'll read that out to you. Evaluation is very long, so I'll read it out. Evaluation of polymer degradation due to aging in asphalt binder and determination of polymer content in asphalt emulsion using an extensional deformation test. This is a part of the project, the development of a standard test method for characterization of asphalt materials and aging-related degradation using an extensional rheometer. You can see that I highlighted that part using an extensional rheometer. This is the unknown part. We use shear rheometer all the time in asphalt binder. So we are evaluating the extensional deformation characteristics of asphalt binder and to fulfill any gap in our current PG specifications. So these are the objectives, and you can see that we are modifying the current method. So as we are developing a new test method, we have been doing this is the third in sequel. The first project we started actually in 2011 with Louisiana DOTD LTRC, where we actually used 20 different emulsions, had the residue, and tried to do the DSR properties, very specifically MSCR, changing the stress levels, and try to correlate it with the Superpave Plus tests, elastic recovery and force ductility that are actually related to extensional deformation, not the shear deformation. So we did that, and we were very close, and our new specifications is actually MSCR based in Louisiana, the proposed new one for replacing elastic recovery. But we did, that was a 3-year project, and we found no good correlation between the force ductility parameters and any of the shear deformation. So force ductility doesn't connect to the DSR properties, whereas the elastic recovery, it really connects to MSCR very good. And there are other state research, several other state agencies, DOT did the research almost the same time in the last 5 to 10 years. So that is also, this is, then we started that when we didn't get correlation R-square value, all of us are familiar, when you try to correlate, there we found that R-square value is 0.5, 0.6 with the force ductility parameter. So what we did actually, we tried to now correlate with the, try to find out how we can capture the extensional information. So we went to a new method how we can use the DSR machine and do the extensional test. We tried rotational test in DSR, it didn't work. So it has to be PU extension test. So we did that one in this here. We presented a new method that actually captures the second peak of second force peak. I'll explain that a little bit later what I mean by second peak. So we were able to characterize that one. And then, so that's the second project. And the third project we're doing is actually with Transat, that we would like to now incorporate in the PG specifications or some of the properties, like for everyone uses polymer nowadays. It's very common, polymer modified binders, and how polymer behavior or how polymer degrades with time. We know that PG tests were developed on neat binder, not the polymer binder. Now everyone using polymer, how that polymer changes. So we rather need to characterize polymer's life and its performance So that's why in this test, this project we initiated where we are doing aging in polymer because that's one of the common degradation process during various life. So we are aging polymer modified binder and we are looking at the force peaks, the first force and the second force and the ratio of the second over first one. I will explain why second over first one. And then also, is this second peak or this type of extensional behavior, does it in any way correlate with the polymer content or not? Can we use that, this test extensively? So as I kind of write this one, after my ascent-minute extensional limiter was introduced for asphalt binder characterization. This is what we came up with that, okay, we'll use that is being used for polymer, we'll use that in our DSI and try to do the extensional deformation test. So we did that, and also we used polymer modified asphalt emulsion that has 0%, 2.5%, 4%, and 5.5% polymer. And we used polymer modified asphalt binder also, which is PG76 minus 22, and we aged that original RDF and PAB aged. Here we just checked how our forces are changing with respect to percent of polymer, so that we can use this test to know how much polymer is there really in the film. And then also this one is how we aging our force peaks changes. So here is the sample matrix where you like look at this one because that will give you the size of the sample. Because we know that the force dart or the elastic recovery sample, it takes a lot of material and you do age that, and then it's a long process and material consuming, labor consuming. So here you can see that our material is really, sample size is really small. Width is 1 millimeter, and then thickness is 0.72 millimeters, so the area is 0.72. And then we change that with the polymer modified asphalt emulsion, where the width is 3 millimeter. When I say polymer modified asphalt emulsion, I do mean that is the residue of the polymer emulsion. So, so this is the area here, this is the area here, and the number of sample is 24, and here 12 samples we used. The temperature, force conductivity, we used usually 4 degrees Celsius, so it's 4 degrees Celsius here. And then here you can see 12 samples, so each temperature we used 3 samples for 0%, 3 samples for 2.5, 3 samples for 4, and 3 samples for 5.5% polymer. That's how we got 3 times 4 these 12 samples. And here for modified binder, we have 1, 2, 3 temperatures, and then we have 3 temperatures, and for each case we use actually 3 samples. So that's why we have here you should have 27. The reason we have 24 instead of 27 samples is that we could not do actually for 0 degrees Celsius we could not do the PABH sample because it actually is very steep for doing extensional test. So that's why instead of 27 we have 24 samples here. So as you can see that we almost followed this previous method, and I'll show you. This is a description. I really want you to show you the process that we followed. So I have lots of pictures. We started with placing the binder into the tin can, right? So and then the binder poured into the silicone mold. So this is the DSR silicone mold. So we know that one. And then you can measure this one. The binder was removed from the silicone mold, so this is the size. And then we have these actually the steel plates that we used. You can say that why this method, steel plate has a constant thickness with 0.72 millimeter. The reason we did that is we tried with DSR to compact it and go to 0.72 exact size, thickness, so that we can take it out from the DSR and use that as a sample preparation method. But DSR is really weak in axial force, and also it takes long time because of the delayed recovery of the binder. So say that you compress the binder using a DSR and precisely you got your thickness for sample preparation method, but later on actually you have to wait for hours to kind of get all the delayed recovery gone. There is a delayed force there. So so that's why we use this one, and then we put again a silicon mat on top of this one. On top of this one, we put a silicon mat. Then we put a glass plate. You can see there is a glass plate here, and then we put load. This is 20 pounds of load on top of that. And then we kept it actually for a long time. Earlier we used actually 12 hours time. We changed that later on. The binder shape after removing the load. So this is the shape. You can see that it looks pretty much circular. It came from a DSR mold. So, and then two pictures, they cracked during the cutting process due to long cooling period. So now we have to cut the samples. Still we are cutting it manually using a sharp edge knife, and then you can see that if you pull it before cutting it, you need to pull it a little bit. If you pull too long, it will crack during cutting. And then if you do short period of pulling, because as you need to cut, and you can see that how it looks, and you understand as you all have some familiarity with dance materials. So as you can see, it's not standing, it's actually lying on the mat, the sample, and cutting the binder to the desired length, so you can cut it. Length is not that important because when you put the sample, you will see that it adjusts the length, perfect length. But the thickness and the width is that you have to do manually, and there's still the critical process we're trying to maintain. Sample with desired dimensions, and then you can see that the thickness has been maintained 3.0, and so this is the test procedure after sample preparation. So this is how we prepared the sample, as you see. And then the environmental control was set to 40 degrees Celsius for this, and we used 3 different temperatures for polymer modified asphalt binder. The soak time was 600 seconds, which is 10 minutes. So what we did is we first reached the temperature, then we waited 10 minutes, right? So and the wait for temperature option was activated to ensure temperature equilibrium. Solid density was set to 1.0 gram per centimeter cube. Final strain was 3.7 radian. So as you'll see a little bit later, the two drums rotate. So you cannot actually continue the rotation because they need to overlap. So you have to limit it within half a rotation or so. Okay, so our maximum strain was 3.7 radian. We went by 0.1 radian, 0.1 radian actually per second. It's not here, so that means it took us 37 seconds only to finish the test. You can see this SER, extensional limiter. It has a smart swap, so you just plug this one in so that it knows that it changed from DSM format to this SER format. So, and then you fix the SER bracket. So this is the SER fixture, the extensional limiter fixture. You screw it up with that, and then so as you can see, so this is your oil, this is your rheometer, this is your rheometer open, and this is the shaft. This is the bracket first. You connect it to this one, and then you connected this shaft, and you have two drums here, and those two drums rotate, as you realize when you see the sample place. You see now. You see that there are two drums, and these are the two drums. So you can see two drums. You place the sample here, and you put the staple here, and then you just plug in the staple here and here. So this height is kind of always fixed. And you can see the length of the sample, 12.75 millimeter. No matter how long you cut, the sample length remains to be the distance between the two staples. So even if you prepare long samples, it will not work. It will work, the force will work between two staples. And that staple distance is fixed because you have two holes for each of the sample. So this is samples get out into the hardness. This is what happens if you put very big samples. And this is a very wide thicknesses. The width is very high, and if you do that at 4 degrees or 0 degrees Celsius, that's what binder is really stiff. So it came out. So what we did actually, so that we can do purity aging, we can do bigger samples, and we can do at low temperatures. Actually, the process has been modified. Now, as it is, it's an existing project, we could actually double-sided tape here, double-sided tape here. Now we can put the sample and then put the staple on top of it. So you put the sample, and then you can see this. You can see the double-sided tape also, the black one, particularly. And then you put the sample, and then you put the clamps of the staples, whatever you say, into it as the way the polymer is tested. And this is the screenshot from the way you put test parameter. Very simple. You can see the test temperature is 40 degrees Celsius. Working time is 600. This is density. This is 3.4 final strain, and this is 0.1 per second strain width. And this is how you control your DSR. You can put the set temperature, or you can put the distance. So this is your this is from T instrument, the way you run DSR. Sample during the extensional deformation test, as you can see, the sample is deforming, and then sample after the end of the test, and this is how it looks like. So I'll show you some results. First peak and second peak elongation forces. I mentioned since the beginning of my presentation there are two force peaks. You can do other properties. You can do viscosity analysis, which is the expression of viscosity through this data. But what we did actually, we are trying to focus on first to find some very specifically force peak, so that we can replace at least some parameters and go quickly. Okay, so the first peak, polymer modified binder is a non-homogeneous material. So when you say about asphalt, it is asphalt binder and polymer. So two things are there. In the elongation force versus shape time graph, if you have not seen ever any force ductility test results, it has, I don't have enough time, so it has two peaks. One is the first F1, which when you see the first force, you have a material and you try to ask the material, try to pull it. So when you first force, maximum force you see, that comes from the asphalt binder itself. Okay, now when it's stretched enough, when you try to tear it apart, the polymer won't at that time. So the second one actually gives you the polymer modulus. The first peak comes from the asphalt modulus. So one is asphalt modulus, one is the polymer modulus. You can calculate polymer from these data, modulus from these data also. And then we use F2 by F1. Why second peak over first peak? I will explain it later in time. So if you don't have any polymer, it looks like you just have one peak image. Okay? If you have polymer, you have the second peak. So you see that this is the first peak, comes from asphalt. This is the second peak, comes from the binder. Okay? So this is another result. Okay? So you can see this is this is for 0% polymer. This is for 2.5% polymer, so it increases. This is for 4% polymer, so it increased. And this is for 5.5% polymer. And okay, now the polymer modified binder, when you do age that, as I said that we don't have at 0 degree, we couldn't do that time when we presented this paper or submitted all these. We didn't have the results for the PAB, it was the problem. So we have the results, and you can see that when this is the original binder, and this is the RT4 aged binder. And you can see the first peak aged, asphalt aged, but the second peak got down a little bit. So we try to interpolate data from here that this is due to the aging. And then this is the data at 40 degrees Celsius. So when you did that, we can see that this is the original binder, this is the RTF aged binder, and the PAB did not show any second for speed. In this case, same thing at higher temperature. This is the original binder, then the RT4, and then the PAE. And then I'll go to move to this one actually directly because I don't have time. This is 0 degrees Celsius. You can see that original binder, if 2 over F1, it reduced. For at 40 degrees Celsius, it reduced. And at 12 degrees Celsius, we are just changing temperature to see if the trend is set. That's why we are changing temperature. But as I can always show you that as you increase temperature, polymer effect is more visible. No matter you do DSR, no matter you do extensional deformation, polymer effect, if you like to find, it's more visible in at high temperature. So as you can see that actually F2 and you significantly. And this is the polymer content. We have the result for different percent of polymer as I showed you, and you can see that we have a good R-square value, but still we have some repeatability issues that we are working on, as you can see the error bar. So we are still working on these ones. Actually done. We use 2 different styles of samples, and we have results with linear to linearly correlates with percent of polymer, and F2 over F1 actually reduces with aging, and there is this project there to show that it reduces polymer degrades with temperature and aging. Thank you very much.